Hey there, Chem Squad. In today's class, we're going to take a look at entropy versus enthalpy in equilibrium systems. Now, we've talked about how to manipulate reactions based on using different types of stresses. And Le Chatelier's principle is one of the guiding principles in terms of telling us what happens when an equilibrium system is subjected to a stress. Now, along the similar idea, um, nature has certain types of stresses, which causes a natural shift. And these natural stresses cannot be influenced by humans. Okay, so we're going to take a look at these two stresses. The first one is called entropy, the second one is called enthalpy. Now, just as a recap, entropy means randomness, okay, or chaos. So if you think about things like solids versus gases, okay, solids have more of a structure, so they're more organized. Gases have less of a structure, molecular structure, and they're more random. So gases have more entropy than solids do. Okay? As a matter of fact, we can basically look at all the different types of states of matter and figure out that solids have the least amount of entropy, okay, while liquids have more entropy, gases have more entropy, and aqueous solutions have more entropy. Now, when we focus on enthalpy, enthalpy is the amount of internal energy in a reaction. And we base that internal energy on the amount of energy the compounds contain. So kind of like potential energy. Okay? If you look at how much potential energy the substances have in the reactants versus the products, we can figure out which side of the reaction has more internal energy. We basically base internal energy on the change of heat energy. Okay, so that's why sometimes you'll see a plus or minus delta sign, delta H sign, which just means change in internal energy. So for us to look at how entropy and enthalpy tie into each other for equilibrium reactions, we do have to find the side of the reaction that has the most randomness. Okay, the most randomness or most entropy are always naturally favored. So we call this maximum entropy. Oops, spelled maximum wrong. Okay. So the side that has maximum entropy is going to be the side that the reaction will shift towards all the time. Now, the side that contains the least amount of energy, okay, internal energy stored in the substances, that's the side that's going to be more naturally favored. This one here is a little bit trickier, okay? But we call the side that has the least amount of internal energy the side that is minimum enthalpy. So we want to find the side that has maximum entropy and the side that has minimum enthalpy. Both these sides are naturally favored, okay, and the reaction will naturally shift to those sides. So it naturally shifts to this side. And because we can't control the amount of randomness, okay, it just depends on the state of the reactants and products, and we can't really control the amount of internal energy or enthalpy, okay, these are two factors that humans cannot influence. So we need to understand, if we can't influence it, we have to figure out, okay, well, what is the side that it will naturally shift towards whenever we make any kind of change. So to give you an example, okay, Here we have a chemical reaction between sodium hydroxide, which is a base, with water. So essentially, we're dissolving sodium hydroxide in water to form sodium ions, hydroxide ions, hydrogen ions, as well as generating some heat. So this reaction itself generates heat. Now, this reaction is technically supposed to be an equilibrium reaction. Okay, so the side going from left to right, from reactants to products, generates heat energy. So it's exothermic. Now, if we looked at the reverse reaction, if we look at how the products turn into reactants, okay, that is an endothermic reaction because the products need to absorb this amount of energy, 125 kilojoules, in order to reform your reactants. So within an equilibrium system involving heat energy, we can look at endothermic reactions and exothermic reactions as well. But let's take this one at a time. Let's look at which side of the reaction has more entropy. Okay, so to discover which side has more entropy, we have to find which side contains more moles of gas and or aqueous. Okay, so obviously on the reactant side, we have 0 moles of gas or aqueous. And on the product side, we have 1 plus 2 is 3 plus 1 is 4 moles of gas or aqueous. Okay, so that means the product side here are more random. Okay, because their states are more random. So the product side has maximum entropy. So the reaction, if you're only basing it on entropy, it'll be shifting towards the product side naturally. Okay, so there's a greater likelihood of forming products than reactants based just on entropy. But because we also have to look at energy, okay, internal energy. Now, like I said, this is the trickier one to understand. So I'm going to switch colors here to perhaps red. If we look at our original definition of internal energy, we need to find out how much energy is in the compounds in terms of what we're looking at. So here's the thing. If we look at your reactants, when your reactants turn into products, they're releasing (125 kilojoules of heat. Okay, so if 125 kilojoules of heat is being released when you go into the forward reaction, that means these substances here lack 125 kilojoules of energy. Okay, so from last year, we know that in an exothermic reaction, heat energy on the product side usually means that heat energy is released. Okay, now the other thing that you have to realize too is, if we look at the reverse reaction, these substances will have to absorb 125 kilojoules of energy in order to form your reactants. Okay, so these reactants actually contain 125 kilojoules of energy more than the products. So because the products have less internal energy, they have minimum enthalpy. So products contain less internal energy than reactants. Okay. Therefore, the products therefore the products have minimum enthalpy. And if the products have minimum enthalpy, the reaction will again naturally shift to the product side based on enthalpy. So together, both factors tend to shift to the product side. So both factors favor the product side. So this reaction, the forward reaction, is more likely to occur than the reverse reaction. So forward reaction more likely to occur at equilibrium. Okay, so at equilibrium we can perhaps expect more products than reactants because of these two factors. So let's take a look at a different example and see how you guys do with this one. So again, I want you to identify which side has max entropy, which side has minimum enthalpy. Oops. So let's do it like this. So let's look at entropy. On this side here, we have 2 moles of aqueous, okay, because we don't count the solid. On the other side, we also have 2 moles of aqueous or gas. Okay, so in this situation, both sides are equal in entropy. Okay, if we're only looking at the number of moles of aqueous and or gases. So everything is based on enthalpy now. So we want to find the side that has minimum enthalpy. Okay, so when we again look at this equilibrium reaction, okay, if you're going forward, okay, from reactants to products, the reactants have to gain 225 kilojoules of heat energy. So that means the products contain 225 kilojoules. Okay. If you're going in the reverse reaction, the products, when they reform the reactants, they get rid of 225 kilojoules of energy. So your reactants loses 225 kilojoules. So one of the easier things to do, okay, if you can't understand the concept of which side has more heat energy, okay, internal heat energy compared to the other, is to look at which side contains the heat. Okay, the heat is found on the reactant side. Therefore, the reactants have less internal energy. Okay, so the reactant side is minimum enthalpy. So because the side that has minimum enthalpy is favored, okay, what we can say from the information that we have is that the reaction will naturally shift to the reactant side. And this is solely based on minimum enthalpy, because maximum entropy didn't favor either side in any way. Okay, they're both equally as random. So it was up to looking at minimum enthalpy to see which side the reaction will shift towards. So let's look at the final example here. Okay, so same kind of scenario. We want to find out which side has maximum entropy and which side has minimum enthalpy. Okay. So again, entropy is the easier one to do. On the reactant side, we have 0 moles of gas or aqueous, and on the product side, we have 1 mole of gas. Okay, in this case, carbon dioxide gas. So this is a combustion reaction. So you have a hydrocarbon, okay, in this case, liquid methanol, and it requires heat to be added in order to form water and carbon dioxide. So based on the states in this equilibrium reaction, maximum entropy goes to the side of the products. So products favored, or product side is favored. Okay. In terms of minimum enthalpy, energy is found on the reactant side. Okay, so this means that the reactants loses 56 kilojoules of heat energy. So the reactants reactant side is favored because it has minimum enthalpy. So again, the way that we look at this is, if we're looking at the reverse reaction, you are basically creating CH3OH, but at the same time, you're giving off 56 kilojoules of heat, okay, when we're making the reactants. So the reactants have less heat energy than the products do. So because your minimum enthalpy favors the reactant side, but your maximum entropy favors the product, overall, we cannot determine definitively which side is favored. Okay. We need more information. Okay, and we just don't have that given to us in the current state. So it just seems like we have, based on entropy, the product side is favored, but based on enthalpy, the reactant side is favored. So when we have these two natural forces on either side, overall, we cannot determine which side is normally favored at equilibrium. We'll actually need to run some more tests and look at some other factors in order to figure that one out. So in terms of our scope for grade 12, we kind of just leave it at that we cannot determine which side is favored. So it's important for us to be able to at least identify which side has maximum entropy and which side has minimum enthalpy. Okay, so to summarize, all of your equilibrium systems, okay, that I give you, when I ask you for which side is naturally favored, always start thinking about minimum enthalpy and maximum entropy and see where the information takes you from there. All right, that's all that I have for today. Hope to see you guys soon. Thank you. Bye.